Hey guys, in all the examples that we've talked about so far, if we've written the rate law, the rate is equal to, let's say, k times a to some power times b to another power. When we looked at the experimental data for that, we had different trials. Different trials which showed us how if we change the concentrations of a and b, we could derive experimentally the order of the reaction. And in all of those cases, we said that K was constant. And that's true because we performed them all at the same temperature. However, if you change the temperature at which a reaction occurs, you affect its rate, and the way you affect its rate is because you're actually changing K. So K is only good for one particular temperature for each reaction. So you might wonder, how do reactions change when you increase the temperature? Well, if you really think about how reactions occur, two atoms or molecules have to smack into each other. The higher the temperature, the higher the speed the molecules have, and the more likely you are to have a reaction. They're going to collide more frequently, and when they do collide, they collide with more power. That's because K, the reaction constant, is equal to A, what's called the, it's related to collision frequency, times E to the minus EA over RT. So K breaks down into these different values. Let's talk about the EA part first, the activation energy. The activation energy is the energy needed, the minimal energy needed for a reaction to occur when two molecules collide. So then that depends on the molecules themselves. So if these two molecules collide slowly, they probably won't climb the activation barrier they need to climb, the energy barrier needed to climb for the reaction to occur. But if they collide quickly and with a lot of oomph, then they will probably meet the minimum activation energy needed for the reaction to happen. Because all reactions have to climb a certain energy barrier for that thing to happen, for that reaction to be productive. That's what EA represents. A represents what's called the frequency factor. Frequency factor. And that's related to the orientation of the molecules in 3D space. If molecules are using p orbitals, for example, and they have to collide and their electrons have to touch in a particular set of p orbitals, because the orbitals have different orientations, just because they smack together with the minimum energy, as dictated by the activation energy, doesn't mean that it's going to be productive. The orbitals may have to be pointing in a certain way in order for electrons to overlap. Now, s orbitals being spherical would have a much easier time being productive because there's really no sort of spatial orientation requirements if they're spherical. But if you've got something like p orbitals or d orbitals that are only pointing in certain directions, not every reaction is going to be productive. So that's what the frequency factor deals with. And R is the gas constant, and T is the temperature in Kelvin. So let's look at this just a little bit more closely. And let's see if we can mess with this equation a little bit and get rid of the E. So I know that natural logs are the inverse of E. So if I take the natural log of both sides of this equation, what I get is this. And if you remember, the natural log of A times B is equal to the natural log of A plus the natural log of B. So that's what I'm going to do here with the A and the E. The ln of K stays the same, but the second part I'm extracting and I'm separating right there. The ln of A plus the ln of E to the minus EA over RT. And when I do that, I get rid of this, right? And all I have left is minus EA divided by RT. Another way to show this is ln of A, or ln of K, I should say, is equal to the ln of A minus EA divided by R times 1 over T. And the reason I say this is because if you graph this as the natural log of K, so you measure the rate constant at different temperatures, and you take the natural log, and you plot that of 1 as 1 over T, what you get is a line. And that line looks like this, and the y-intercept, right, the b value is the ln of A, and the slope, right, the slope, m, is minus EA over R. So you can get the activation energy from the slope of this line. The slope of this line is equal to minus EA over R. R is a constant, so we would factor that in. Because it's a straight line, this equation can be looked at from two different places, right? At temperature 1 and temperature 2. And because you can look at that at two different places, you can derive the following relationship. You can predict what the rate constant will be. So most of the time in this equation, your unknown is the K2, and that's why you're doing it. In this equation, it's equal to minus EA over R times 1 over T2 minus 1 over T1. So if you know the reaction or the rate constant K1 at any given temperature, you can plug in T2, right? So this will be known. This will be known because the question you're saying is, well, if K is equal to, X at temperature 1, what is K2, right? What's the new K at temperature 2? You plug in temperature in Kelvin units. You have your activation energy, which you're either given or you can figure out from the slope of this line. And you have your K1, and then this becomes your unknown here. This becomes the unknown, and this is what you solve for. And just so we're all clear on one more thing, the R we use is 8.314 joules per mole K. This universal gas constant, it's almost always used as 8.314 when we're talking about energy, right? Because it has joules of energy. And when we're talking about it as gases, that's when it's the 0.0821. But because we're using this more in terms of energy, this is the unit that applies here. And so this is the second form of the Arrhenius equation. And you can use this to determine what the new rate constant is. If you have the new rate constant, and you have the original rate constant, you could also use to determine the activation energy. Obviously, we only have one unknown at any one time to solve in these equations. And that is the Arrhenius equation, and that answers the original question of how does changing the temperature affect the reaction rate? As a review, it affects the reaction rate because it affects K, the rate constant. And this equation, the Arrhenius equation, can be expressed in another form like this at two different temperatures. Okay, that's all for today.